Hello everyone. Today I am going to discuss about the nuclear detectors. So nuclear detectors and counters is a instrument which is used to detect the charged particles, to count the charged particles and to compare ionizing power, kinetic energies and many other different properties of charged particles. Okay, so in this video I want to discuss the general principle and working mechanism of this kind of gas filled detectors. So gas filled detectors like gas ionization chamber, proportional counter, Geiger-Müller counter. Okay, we see one by one. Let's begin here. We have a general construction of those kind of nuclear detectors. So here you basically have a metallic cylinder which is hollow from the inside and it filled with some kind of gaseous medium like hydrogen, air at one atomic pressure, and along the center of the cylinder you have metallic electrode which is passing through it. Now this cylinder surface is connected to some negative terminal of voltage supply. Metallic electrode passing through the center is connected to load resistance which is again connected to the positive terminal of the same power supply. Now to prevent this positive metallic electrode from touching the negative metallic surface, there is some kind of insulating material. Now across the load resistor you have some sort of electronic which is connected to it like some kind of an amplifier or pulse counter that can basically detect the potential drop that is happening RL and measure the amount of current which is passing through RL. So what is the principle on this kind of detectors? Based upon it is based upon the principle of ionization. So when high energetic nuclear particles passes through some kind of the material medium, it basically ionizes the material medium. Now what is ionization? It is a quite simple. So let's take the example. Let's suppose an alpha particle which is passing through the some kind of material medium. Alright, now alpha particle is quite energetic and it collides with the molecules and the atoms of that material medium, and every single collision it basically transfer some of its energy to the molecules, the material medium, and this energy is basically absorbed by the electrons in the outermost shell of these atoms and molecules, and if the energy is sufficient enough, the electrons will absorb that energy, okay, and become free from the atoms and molecules, thus creating a positive ions and a free electrons. That means formation of ions. Now this kind of collision happens many number of times. So along the trajectory of alpha particle on other high energetic beta particles or gamma particles, due to many number of collisions, large numbers of pairs of positive ions and free electrons are created. So when a nuclear particles enters material medium, basically leads creation of pairs of ions and free electrons. The greater the energy of the nuclear particles, the longer is going to be the ionization and larger is going to be the number of positive ions and free electrons which are created. Now what happens when these positive ions and free electrons are created in the first place? They are subjected to an external electric field. So as you can see here, the metallic surface connected to the negative terminal of the battery while the metallic electrode passing through the center is connected to the positive terminal. So basically you end up getting an electric field along this particular direction. So you will get an electric field which is directed from the metallic electrode towards a metallic surface. So every time some kind of external nuclear radiation enters this material medium and leads to creation of an positive ions and free electrons, when these charged particles are now subjected to this electric field, so what happens is that these electrons will now experience an electric field towards the metallic electrode, okay, and experience a force, where force is basically given by if the electric charge multiplied by electric field, and then it will accelerate towards the electrode, while the positive charge will be accelerated towards the metallic surface. So all the ions and free electrons which are created during the primary ionization process, when an external nuclear radiation interacts with the material medium, so these primary ions will be attracted towards opposite polarities of metallic electrode and metallic surface. So after some time, all of these free ions which were created will get accumulated along the metallic electrode. And as well as the metallic surfaces. And all these electrons which get accumulate on the metallic electrode travel through the circuit. They basically leads to a potential drop across RL, and this potential drop across RL is detected by the electronics as a proof of the existence of an external nuclear particle. So the electrons complete the circuit and then get absorbed by the positive ions, which become neutral again, thus bringing the entire configuration back to its original state. Now it is important to note that the size of the current pulse which is detected across this load resistance, it depends upon the energy of the incident radiation. Why? Because if the energy of the incident radiation is very high, then that would lead to a huge amount of ionization, which will create a large number of electrons and free electrons, which will end up creating a greater amount of current, thus leading to bigger current signal. So bigger current pulse will automatically mean that the energy of the incident radiation is greater, and the smaller current pulse will mean the energy of the incident radiation is lesser. Now there is another variable is involved here, the voltage of the battery. What happens this particular process when the change voltage of the particular battery? So do understand how the size of the current pulse changes with respect to the voltage of the battery, and as well as the energy of the incident radiations. Let's look at this particular graph here to understand how the size of the current pulse changes with applied voltage, and also to the distinguish between kinds of nuclear detectors like ionization chamber, proportional counter and GM counter. Let's look at this graph. Alright, so in the x-axis you have the applied voltage of the battery, and in the y-axis you have the log of the pulse size. Now when the voltage is very less in that case the electric field will be very low, and the electrons and the ion produced by the ionization will not experience huge amount of the acceleration. Therefore, what is going to happen is that due to the thermal motion, these electrons and the positive ions will come back together and recombine to form neutral atoms. This process is known as recombination. So recombination is a process in which the ions created by the ionization due to some external particle due to the thermal motion come back together and recombine to form neutral atoms. So once they have becomes neutral atoms, they are useless and they not contribute towards the current in the load resistance at all. So when voltage is very less, recombination is quite dominant, but when the voltage of battery is increased, then recombination becomes less and less because the movement electrons and ions are formed, they start getting accelerated towards the opposite terminals of this detector. So what happens is that when you have increase in voltage, the current pulse also increase along with it. So this dotted line basically represents that particular voltage in which recombination becomes almost near about negligible. Okay, and all the electrons and ions created during primary ionization basically end up contributing towards the current pulse. So this is the maximum current pulse possible due to the primary ionization, and further increase in voltage will not contribute towards the increase in the current signal. So first region is distinguishable by the presence of recombination, and increasing the voltage decreases the recombination, and we end up getting a maximum current size possible for a particular energy of the nuclear radiation. Now I also want to distinguish between two situations. One situations where nuclear radiation has an energy of E1, and second situation where the nuclear radiation has energy of E2. Let's suppose E2 is greater than E1. How? What is going to happen for the case of particle having energy greater than this particle? In the case, the ionization is going to be greater, so the number of ions will be created longer in the case of E2, okay, as compared to the E1. You will see the same sort of behavior for the second particle. However, the current pulse will be greater for the second particle with increase in voltage. So as you can see here in the region, number 1 with increase in voltage, every combination decreases and we end up reaching the maximum possible current pulse for the primary ionization cost. However, for greater energy of the incident particle, the current pulse will be greater in the second region. As you can see here, recombination is near about 0 and the current pulse is purely dependent upon the energy of incident radiation, and it is not dependent upon in any further variations in the voltage of the battery itself. So this region is distinguished by ionization chamber. So ionization chamber works in region number to where the combination is near about 0, and any change in voltage within this region does not change the current pulse at all. Rather, the size of the current pulse is purely depend upon the kinetic energy of the incident particle. So, greater the size of the current pulse, greater is going to be kinetic energy of the incident particle. This kind of a nuclear detector is basically used to detect high energetic alpha particles, beta particles or gamma radiations. Now, what is going to happen if further increase the voltage of this particular system? If we further increase the voltage in this particular situations, are very different kinds of behavior at different kinds of mechanism seen. What happens is that when electrons are created during the primary ionization, they are accelerated to as positive anode of the system. Now, if the voltage potential difference is extremely high, then their electrons will also further leads to secondary ionization. That means these electrons and ions, when they get accelerated towards opposite polarities, they will also collide with the molecules of the medium and lead to further ionization. So, are known as secondary ionization. So, there is going to be cumulative addition to the total number of positive ions, and electron due to the secondary ionization happening because of this collision due to the electrons at positive ions at the first place. So as we increase the voltage, further the energy of the electrons and the ions becomes so high that they themselves causes secondary ionization, thus increasing the total number of ions and leading to an increase in the current pulse itself. What we end up seeing is that the current pulse increases linearly with respect to voltage. So this region of what is known as proportionality, so this is proportional region where increasing voltage leads to a proportional increase in the size of the current pulse itself. Now, this region is very much important for low energetic nuclear particles. If the nuclear particles incident on this system are very less energetic and they are not able to induce sufficient amount of ionization, then the current pulse created will be so small that it will be difficult to differentiate from the electronic noise. In those cases, for particles having very low energy, we want to increase the signal of the current pulse process itself. In those cases, it's better to increase the voltage so that the current pulse itself will increase with increase in the voltage, and we can distinguish the current pulse from the electronic noise. Now, how can you distinguish two particles from each other for this particular region? Since there is proportionality for both these particles will have current pulse which will increase proportional to the voltage, and we can distinguish both of these two particles because having different energies. So this is a region of proportionality, and the detectors which work in the proportionality region are known as proportional counter. They are basically used to detect less energetic particles where the particles does not have sufficient kinetic energy to lead primary ionization, and that can create current pulses which can be distinguished from electronic noise. We increase the voltage so that the primary ionization leads to secondary ionization, and that leads to cumulative increase in the size of the current pulse self, what happens if we further increases the voltage? Further increase in the voltage will lead to a sort and avalanche effect. So what is mean by avalanche effect? In physics, a sudden increase in the flow of an electrical current through a non-conducting or semiconducting solid when a sufficiently strong electrical force is applied. Okay, and the primary ion create for the secondary ions further creates the tertiary ions. They will create the further ions. A chain reactions will happen which will lead to an avalanche effect. This avalanche effect, we increase the total number of ionization happening. So what is going to happen is that we will end up going to a region where there is a limited proportionality. That means proportionality of the increase of the current pulse with respect to the voltage will be destroyed, and we end up reaching a particular situation where with sufficient voltage even one less energetic electron can lead to an avalanche across the entire chamber of the nuclear detector, so that you end up getting the what is known as plateau region. So in the plateau region, even a small less energetic particle can create an avalanche effect along the entire chamber itself, thus leading to a huge amount of current pulse corresponding to that particle. Now as you can see here, the plateau region, we end up getting only one signal particular corresponding to the ionization of the entire chamber. So therefore we cannot distinguish between a low energetic and high energetic particle, because both of them will create the same amount of the current pulse. So this region is basically known as plateau region, and nuclear detector which works in this region is known as Geiger-Müller counter. So GM counters cannot distinguish between the energy of the different particles, but they are very good counting the number of particles which enters a particular nuclear detector. Beyond this region we do not want to go, because further increase in the voltage, it basically lead to a situation where even the absence of any kind of nuclear particle will lead to electronic discharge, which is not favorable at all. So you can see from this graph, ionization chamber basically work in a region where recombination is very less, and the only ionization that is happening is primary ionization. They are very good for detecting high energetic particles. Proportional counter basically working region where there is secondary ionization happening, but the secondary ionization is such that the increase in voltage would only lead to a proportional increase in the current pulse itself. This is basically region used for detecting the less energetic particles. And lastly we have the GM counter region, in which the presence of even a tiny particles having less an energy can create an avalanche effect in the entire chamber. So it's all about the gas filled detector. I hope you have learned to distinguish between different kinds of these nuclear detectors based on this graph.